of a generic, when I'm trying to find the average of anything, it's the, if I want to find average x, it's going to be x times some distribution of it, the x divided by the integral of generically. So we're left with this integral right here. So if we plug in the distribution function over there, I get, well, let me just put the constant out front. So I got 4 pi m over 2 pi kBt, that to the 3 halves, is the integral of v cubed e to the negative mv squared over 2 kBt dv. And this is just a simple little integral right here. Okay, perhaps not so simple, but we have an integral here which is definitely within the wheelhouse of this course. Let's give ourselves some running room here. Probably should have written that not in the middle of the board. No, thank you. So my frequency distribution as a function of the speed is 4 pi m over 2 pi kBt to the 3 halves v squared e to the negative m v squared 2 t. Now, this is a whole lot of letters right here, and obviously, as physicists, we don't want to write the letters that we don't have to. So what I'm going to do is just a little substitution here. I'm going to let z be m over 2 kBt, just to simplify it. So this now becomes, so that would make my frequency distribution equal to 4 pi z over pi to the 3 halves v squared e to the negative z v squared. Just to eliminate a lot of the writing. Double check, got the m over 2 kBt right there, m over 2 kBt right there. Pi still remains, no pi over there. All right. So my integral over there becomes 4 pi z over pi to the 3 halves integral v cubed e to the negative z v squared dv. That was all the way in the middle. Any ideas how to solve that? What would you set u equal to?
The exponent.
The exponent? Oh, the zv squared?
Yeah.
All right, we can narrow it down. I'm gonna let u equal just v squared. I'm gonna keep the z in there. I think it'll save time in the end. All right, so u is equal to v squared. Therefore, du is equal to 2v dv. And so v dv, 1/2 du. So we have 4 pi z over pi to the 3 halves times 1/2 Now I have a VDV here, but I don't, so I'm gonna break this up into a V squared times V. So there's my VDV. So we get the 1/2 du. And then I have a V squared, which is just u. I'll do it the more traditional way. And then e to the negative ZU. And we're taking this is actually from 0 to infinity. Now what? If we had gone with what you had said, let it equal the exponent, then there would just be a z would show out over here.
Is that integration by part?
Integration by parts is the way to go on this one. So what would you do for the parts?
So u would equal u. Quite
What do we do? No, we're using m over there. R and S.
Alright, so r would be u.
That would be ds.
Yes, yeah.
So dr equals du. S equals
Is that negative z?
is it negative z?
Negative z e to the negative zu?
If we went the other way, if I took the derivative, would I get this? I would actually have a z squared there. It's not z.
Oh. Is it ln?
No, not a natural log,
Okay, never mind.
but you see the ballpark. When I take the derivative of this, I take its chain rule, so I get this, and then I take the derivative of that, and I get a negative z. So I want that to go away because there's nothing up front there, so it's 1 over z.
Okay.
Sorry to spoil that.
No, I appreciate it.
Sure. All right, so does that get us anywhere? So we now have, so we have the integral of r ds should be equal to rs minus the integral of s dr. So we have the integral of, well, basically, we're looking at this piece right here. So that should be equal to rs, which is negative u over z, e to the negative zu, minus the integral of e to the negative zu no. Yeah. SDR du. And now a quick check to see if I made a careless error there. I've got RDS. I lost my, so plus 1 over z. So rs minus integral of s dr. I think that's right.
I think so.
Alright. So now we're left with this.
Which was our DS, so.
Yeah.
So I get negative u over z, e to the negative z u, oh, from 0 to infinity, minus 1 over z squared, e to the negative z u from 0 to infinity.
Isn't that last one effectively 0? The integral,
It what?
because it's e to the basically negative infinity,
Okay.
and then divide, which is basically 0, right?
Okay, so when you plug the infinity in, yes, you get 0.
And then minus 0.
No,
Oh,
not minus 0. Alright, and again, we're just working on the integral, we still have this constant out front that we have to bring back into it. Alright, so we stick an infinity into here, and we get negative infinity, e to the negative infinity. How does that converge? So if I have infinity, and I understand for the math purists out there, this is horrible notation, e to the negative infinity